Good morning, ladies and gentlemen. This is Ben Keyser with Applied Flow Technology, and I would like to thank each and every one of you for joining in on today's webinar with us. And it's great to have you all here, and I hope that you all are having a fine week. And today, I'm excited to do a webinar for you all regarding AFT Extreme. AFT Extreme is a brand new software tool that we have just released earlier this year that we are very excited about. And AFT Extreme does gas hammer and steam hammer analysis for gas piping systems. And so it's built off of the powerful thermodynamic performance equations with AFT Arrow and uses the method of characteristics known for AFT impulse. And with their powers combined, we have AFT Extreme. And so, in case you're not familiar with all of the different software tools that we provide, I want to encourage you all to go to our website at some point when you have the time, and that's aft.com. And then under the products menu, just go to software overview. And this is where you can find all of our software tools in one spot. So we have AFT Fathom for liquid piping systems for steady state, AFT Arrow for gas piping systems in steady state. Then AFT Impulse does water hammer and surge analysis for liquid piping systems. And AFT Extreme does gas hammer and steam hammer for gas piping systems. And if you notice, each product has a number of add-on modules that are available that can enhance your flow modeling capabilities. And they're really useful, and there's a lot of areas that they can bring great benefit. And so I would encourage you to take a look at those and see how they would be able to help you with your specific applications as well. So what am I talking about today? First off, I'm going to demonstrate a completed AFT Arrow model where we did a steady state compressible flow analysis. And what is really helpful with our software is that all of the interfaces are virtually the same. So when you learn one of them, you have a really good idea of how to use the others. The other advantage is you can open up a AFT model in any AFT application. So I'm going to demonstrate how to open up a AFT Arrow model in AFT Extreme so that you can then do a gas transient analysis. One other thing I want to mention is that AFT Extreme does have an add-on module as well, pulsation frequency analysis, that will do a acoustic study for looking for resonance in compressor systems. So if you have a lot of pulsation issues, then the PFA module can be really helpful that you might want to take a look at that. All right, so let me go ahead and get into it. Here is AFT Extreme and here is AFT Arrow. So I'm going to start off by opening up my AFT Arrow model. And there we go. Now, this is not a model that I built from scratch. If you have access to AFT Arrow, you have access to this model file as well. So if you go to the help menu and then show examples and pick your favorite units, this will open up the help file that contains all of the walkthrough tutorials that will help teach you how to use AFT Arrow. And so the example that I'm starting with is this one right here called the compressed air system. So that's what I'm modeling here. This is a great example in AFT Arrow that has you make great use of working with the scenario manager, modeling heat transfer for steady state, etc. And so essentially what this example is modeling is the delivery of air to various tools. Maybe this is some sort of manufacturing process, and you've got a compressor here, and you're doing a heat transfer study because the tools are temperature sensitive. So one of the uh, problems that you need to figure out is what is the delivery temperatures for each of the tools. So you look at several different cases, such as a case where there's lots of heat, and then you have a case where there's lots of cooling to determine what the minimum and maximum temperatures would be. The input for the system is fairly simple. As you can see, we've got some 25-foot long pipes, 10-foot long pipes, all ranging between 1 and 2 inches in diameter. And I'll just go ahead and go to the example right now. We have atmospheric air coming in at 0 degrees or 0 psig and 110 degrees Fahrenheit. So the base scenario is starting with the hot scenario. And so when we evaluated the different cases, the hot case is basically a identical copy of the base scenario. And so if you look at this and open up the pipes, you can see that there would be heat transfer. Now here's the thing. AFT Arrow can do full heat transfer analysis, convection, conduction through pipe walls. You can add layers of insulation, etc. It's all there. But the thing is, currently AFT Extreme currently assumes adiabatic or isothermal processes. And so in the first version, it's not modeling heat transfer yet in AFT Extreme, but it will later. And so the reason why I listed this as adiabatic is because I want to make sure that my results in the steady state from Arrow are matching the steady state results in AFT Extreme. So that's why heat transfer is being ignored in the base scenario by me. And so we have our compressor here, and we have a compressor curve, and we are assuming a adiabatic compression process, which would be 100% efficiency. We will see an increase in temperature across the compressor because of that. And the tools, or valves rather, are simply discharging into atmospheric air, 0 psig, 70 degrees Fahrenheit, and I assumed a CV value of 20 and a XT value of 0.7. And so that's the case for all of the tools. And so after we run the model, we've got results here. I'm going to hide my quick access panel. And what we want to look at is the delivery conditions. So that would be in pipes 6, 7, 8, and 9. So if we take a look at pipes 6, 7, 8, and 9, you have exit velocities ranging from 339 up to 392. And so those are some fairly fast velocities there. Discharge pressures, we're looking at slightly above atmospheric pressure. And then our delivery temperatures here are about 185 degrees. How is that? I'm coming in at 0 psig and 110 degrees Fahrenheit, and I'm discharging at the outlet of the system at about 185 degrees Fahrenheit. Well, it's the adiabatic compression process that is increasing the temperature. When you increase the pressure across the compressor, you increase the temperature. So here we can see that we're coming in at a temperature of 110 degrees Fahrenheit, 97 if you're looking at static conditions, and that temperature is increasing up to 190 degrees Fahrenheit static temperature. So that's why we have these really high temperatures at the outlet. And this is one of the things that we wanted to know. Now, Another way to display the results, which is a lot more useful, is the visual report window. And so the visual report window allows you to show all of your output data right on top of the model itself. I have chosen to show the units in a legend. That way it's not as cluttered up in here. So when you take a look at some of these important parameters, I've got mass flow rate, velocity, Mach number, static pressure, and static temperature. This makes it really easy to be able to see exactly what the conditions are all throughout the system. So here are your delivery pressures, and here are your delivery temperatures. And then the flows range from 500 pounds per hour up to about 611. And we are not traveling anywhere close to sonic conditions, but we could. It just depends on the situation, and Arrow will handle all that naturally for you. Give me 1 second. Okay. So now that I have done my steady state analysis and I understand what my delivery conditions are to all of the tools, this is where I want to do a gas hammer analysis. And what I want to understand is if I was to slam these valves shut, what kind of pressure and temperature surge am I going to see throughout the system? And so that's a very useful application for AFT Extreme. All right. So let me go ahead and open up AFT Extreme now. And when you import a AFT model into another AFT application, it's very simple. All you do is go to File, Open, then browse to the folder where your model is, and you can see here that the default file name is to look for AFT Extreme models. Well, you can also set it to look for AFT Arrow models or anything. And so it's the compressed air system here. I already previously imported this, and so I'm not going to do it again. I'm going to go straight to the AFT Extreme model, which I've already ran and generated results for. All right, so let me walk you through the process of what I did when I first brought the Arrow model into Extreme. Originally, I was in the base scenario. And so in the base scenario, this is where I was trying to match up the steady state results with AFT Arrow first. So because of some of the assumptions of AFT Extreme, such as adiabatic processes or isothermal, if I open up the pipe, as you can see here, there's no heat transfer tab. And so at this point in time, AFT Extreme is assuming adiabatic flow. So that's where I had to make the modification in my Arrow model to make all of the pipes adiabatic so that the results would be able to match. Next was the compressor. The compressor currently assumes adiabatic compression process thermodynamics. And so this was another change that I had to make in the AFT Arrow model to ensure that the compressor was using adiabatic rather than determining from efficiency data. So that was another modification that I made. And then originally in the Arrow models, I believe that the help file example says that to use K factors. And in AFT Extreme, K factor is not an option. KV is, but that's not the same thing as a K factor. That is essentially a equivalent of CV values, but in metric units. So what I did was in AFT Arrow, I started with using K factors, and then when I ran the model in the valve summary, based upon the K factor, I looked at, or I determined what the CV value was, and then I used that directly. So that was another modification I had made. Give me 1 second. Excuse me. All right. So after I went through those modifications, the next thing is the analysis setup. Okay. Now the analysis setup is something that's brand new in AFT Extreme, and you're gonna see this in our next versions for Fathom 12, Arrow 9, and Impulse 9. So if you remember, when you are just starting off in a model and you're not sure where to go, the status light starts the yellow brick road of the process, and it will guide you through every step of the way. And if you are familiar, if you click on that status light, previously it would open up a checklist of items that you would see right here. And those checklist items would need to be completed before you can run a model and get results. And so in AFT Extreme, we don't have the checklist there anymore. Instead of individual checklist items, we basically made it a little bit more efficient and easier for you by rolling it all into a single window. So essentially, this is your checklist, and you want to make sure that you have all green check marks. Once you have all green check marks, then you can run your model. So let's walk through this. Again, keep in mind, I'm in the base scenario, and the base scenario, my intent was just to be able to match arrow results with extreme results before I did my transient study. So what do? Well, first thing, I picked my simulation mode, and I chose to use AFT Arrow Steady. So this is using the same marching methods to solve the network of mass, momentum, energy balance, equation of state, and Mach number equations all throughout the network. And so it's using the same solver as AFT Arrow in that case. So that's the first thing, check mark, nice and easy to get. The second step is to determine what I want to use for the AFT Arrow Steady solution control. And this comes right in from AFT Arrow. It's the same solution methods and tolerances. And I basically use the same thing as an Arrow. So all of this stuff here is nothing different than the steady state solution control that you would see in Arrow. So if I was to open up the solution control here in Arrow, as you can see, it's basically the same. All right. Third step is the method of characteristics steady solution. So AFT Extreme has multiple solvers. For the steady state solver, it's using the same Newton-Raphson method that AFT Arrow uses, as well as the marching methods to calculate all the conditions down the pipes. Now, the method for doing the transient analysis in AFT Extreme, that is different, and that is what you need AFT Extreme for, and it's going to use the method of characteristics. And that's what MOC stands for, is method of characteristics. And method of characteristics is a numerical approach to doing transient analysis. It's the engine that's used in AFT Impulse with some modifications that are required for handling compressible flow. And so the thing is, if we were to use the method of characteristics for solving the transient mass and momentum and energy balance equations and whatnot, if that's a different method than using the Newton-Raphson method here, these solutions should be equal and they should give the same results. And that way you would know if you truly have a steady state. Why is this important? It's important because before AFT Arrow uses the method of characteristics for doing the transient analysis, it needs to have initial conditions for pressures, flow rates, temperatures, velocities, densities, everything all throughout your system for time zero. Okay. And in order to establish those initial conditions, we run AFT Extreme using AFT Arrow's steady state solution method. After we run that with the steady state solution method to get initial conditions, if I was doing a transient, we would then run the simulation again, but instead of using the Newton-Raphson solver, we're using the method of characteristics solver, where we're ignoring all the transients, like we're ignoring valve closures or compressor trips, etc., for the first time zero time step. So it's a pseudo steady state run. So if we don't make any changes in the transient, we should see the same results. And the key thing is, if you see a difference in steady state results between these two solution methods, that's going to cause what's called an artificial transient. It's going to make things start happening in your system that is not really there, and that will corrupt your results. So you want to make sure that those results are as close to each other as you can have them, and there is some tolerance criteria here that dictates how steady is steady enough. Now, I'm not going to get into all those details and how to do that in this webinar, but this is one of the steps that I had to do. All right, fourth step is the fluid. This is the same thing as AFT Arrow, where you just pick the gas that you want to work with and you add it to the model. That's all there is to it. And then environmental properties, this is just your atmospheric pressure, transitional Reynolds numbers, etc. So since I'm only doing a steady state run, all of this is done. I don't have to bother with doing these steps yet, so I can ignore those. And when I click cancel, I already ran the model and I've got results. If I change these mass flow rates to pounds per hour, and I take a look at my visual report here, move this around a little bit. There we go. All right, so let's spot check some results. Looks like I'm missing my mass flow rate. Let me put my mass flow rate back on there. There we go. All right, so let's compare. I have 2163 as the total mass flow coming into the system. Let's check AFT Arrow. 2163, that looks good. Let's check the flow rates coming out of the tools. So I've got 611, 542, 509, and 500. So in AFT Extreme, I have 611, 542, 509, and 500. It's pretty good. Let's look at the outlet temperatures. 183, 185, 186, and 187. If I go back to my AFT Arrow model, I've got 183, 185, 186, and 187. Excellent. So basically, this confirms that the AFT Arrow results for steady state and the AFT Extreme results for steady state are consistent with each other. So I have the same model, everything's good. All right, this is where I then went in and I created my transient case. Now, this is where you have to do some additional steps. All right, so the first thing that we need to do is in our analysis setup window, we would first need to turn on MOC transient. So when you turn on MOC transient, again, that just stands for method of characteristics, and it's going to do the transient analysis for our simulation. And these are the next three items that would need to be completed. So here in sectioning, this is where we have to section the pipes and break the pipes up into bits for the transient calculations. And then the MOC transient, this is where you define how long you want to do a simulation for. So I'm doing a 5-second transient simulation. Now, I will forewarn you that the transient solver process for AFT Extreme models can be very long. And the reason for that is because this is matching much more like a regular finite difference approach type of solver, where you need to have a lot of sections in order to have more accuracy. This is something that is very different from AFT Impulse. In AFT Impulse for water hammer analysis, you don't have to have millions of sections in order to get an accurate solution. And so this is a very different concept with AFT Extreme for compressible flow. And again, I'm not going to go into the deep details on how that works, but just know you will probably find yourself needing more sections and having longer run times. And this is where it's even more important for you to do a sensitivity analysis. If you pay close attention, you can see here that I have two scenarios: transient case and a one section case. So here's the thing. When I first started running this model, getting it ready, I was running into convergence issues. The reason why is because if you don't have enough sections and if you don't set up your estimated maximum temperature correctly, you can run into convergence issues. And so one of the troubleshooting approaches is to add more sections and to increase your estimated maximum pipe temperature during the transient. Now, again, I'm not going to get into the depths of that. Definitely be sure to read the help file, the documentation. That goes into a lot more detail of what's going on and why you would need to change these values. After I did, so when I set this sectioning up here, I'm not going to run this example. I'm not going to click OK because I don't want to wipe out my results. This scenario took 46 hours to run. Okay, and so this is just the nature of what you're going to need to get used to with AFT Extreme is much longer run times because of the nature of compressible flow and how the method of characteristics works. We're working on ways to improve that, but ultimately it all comes down to sectioning. Well, after I ran that 46-hour long scenario, I then ran it with one section. I figured out what I was doing wrong. I didn't have a high enough maximum temperature estimate, and running it with one section, the results were virtually identical to the transient case for 46 hours. But that's not always the case though, and it's not always conservative. And so what you can possibly find is adding more sections, you might see higher pressures and higher temperatures, maybe not just high, but larger extremes in temperatures and pressures. So it's not always conservative. So be sure to do that sensitivity analysis to see what you're dealing with for your specific system. And it really is a thing that is system specific. For some systems, it might cause long run times. Some systems, maybe not so much. All right, what transients am I doing here? I'm doing my sudden valve closures. So what I've done is I've started with the valve being fully open, and I'm closing the valve in 0.2 seconds. Now I've done staggered closures. So each valve closes within 0.2 seconds, but they are staggered. So this valve closes first, this valve closes second. So as you can see here, for the first data point, it's staying open, no changes. And then at 0.2 seconds, that's when it starts to close, and it closes within 0.2 seconds. If I go all the way out to opening up the last valve here, you can see that it's open for the first 0.6 seconds, and that's when it starts to close, and it closes by 0.8 seconds. So everything is closed by 1 second, and I am running the simulation for a total of 5 seconds to see what happens. Now with that, I'm going to go to the 1 section case. That way it runs a little bit faster, it shows things a little bit faster. So after running the model, here are the results that we see. We have a warning message that talks about how the compressor has reverse flow during the transient. Definitely something that you want to make sure that you avoid. We will look at that here in a minute. And then we have our pipe results and our junction results. And so the junction results, these are all steady state, so I'm going to collapse that. These are the transient maximum and minimum. So these are the maximum pressures that you see, minimum pressures that you see, maximum flow rates, minimum flow rates, etc. These are the steady state results. For the transient output, you can expand the all the different pipe stations, and the slider bar is your time step. But you know, if you're familiar with transient modeling with our software, looking at things in tables is not really going to be very helpful for you at all. So we're going to look at graphs for that. Now, one of the things that is really helpful are the event messages. So this tells you when things are happening. So this is a good thing to check first. So here, this tells me what events are happening in chronological order, and you can see that you do have sonic choking. Isn't this interesting? In the AFT Arrow model, if you look at the output and on the top tab here, there are no sonic choking tabs. That means that there is no sonic choking during the steady state conditions of this system. However, when you get to doing the transient analysis, we do have sonic choking. And where is it sonically choked at? It says branch junction 6. Where is that? That is right here. So we have where we're going 2 inches in diameter, and it stays at 2 inches in diameter, but we're going from 2-inch diameter down to 1 inch. And so at some point we do experience sonic choking at the branch here. And so that's something that you would probably want to know. So if you were to right click on the branch, you can generate a graph straight from the workspace itself. And so here, if I right click and I say generate a transient graph for the pipes, here's your various options. And I might want to look at velocity. And then what I also might do is add another parameter for sonic velocity and make that be a secondary y-axis. So here, this is where you can see that your velocities are exceeding that sonic velocity. And this is just something that can happen where you might be sonically choked during the transient, but not your steady state analysis. So this is where you would need AFT Extreme for that. All right, let's look at some results here. First thing, let's take a look at what the pressures and temperatures are at the tools. So that's the outlet of those pipes. I already created a graph for that. That's this one right here, tool, pressure, and temperature. So this shows you what is happening for the pressures and temperatures. So this valve closes first, followed by the second tool, the third tool, and the fourth tool. So you see here that we have the pressure surge at the staggered times. And then as those valves are closed, we are still compressing the system. So that's where we see some increase in pressure here. And then once those valves are fully closed, the pressure settles out pretty quickly. You can also see the temperature effects. So we're going from 190 degrees Fahrenheit up to between 240 and 270 degrees Fahrenheit. So this is something that is important to pay attention to, is what your temperatures are, especially because of the fact that our tools are temperature sensitive. So when you did your steady state analysis, you figured out whatever that maximum temperature was. I think it was 190 degrees Fahrenheit. Well, this clearly shows, wow, if you were to slam those valves shut, you will have some really high temperatures. Doesn't last very long, but is that going to be a problem? Now, obviously, once these valves have been slammed shut, you don't want to keep deadheading your compressor against your closed valves. So that's where I have another scenario where I do a compressor trip and I include a check valve. But before I move on to that, I want to show you one more graph. So here I created a new folder and I included 3 different graphs: a profile plot animation, the check valve CV versus time profile, and the check valve pressure and temperature. Actually, I do need the next scenario for this. So let me load that scenario here. I thought I loaded it. There we go. Okay, so all of the valves here are still closing in the same way that they closed before. But if you remember, I had a warning message that told me that I'm getting some reverse flow through a compressor. Well, what happens in that situation? If the flow decreases to be less than 0, what do we use for the pressure increase across the compressor? Well, we don't have any other good data to go on, so we're going to be using essentially the shutoff value, the deadhead pressure increase, and that may or may not be accurate. It's probably not accurate. And so in the absence of any other data, that's what we use. And so what we're doing here is, in my transients, I'm going to do a compressor trip. So I know that all the valves are going to be closed by 1 second. So it stays at 100% speed for that first second, and then the compressor shuts off within a second. So that's a pretty quick compressor trip there. And then here's my check valve. And the check valve, this is using a more simplified model just to keep things simple. So I did a K factor where it's going to close based upon a 0 velocity. So once the velocity in the pipe that is immediately downstream, basically right here, the inlet of pipe 10, once the velocity drops to 0, that's when the check valve is going to slam shut. In order for a check valve to reopen, we would have to have a pressure difference of 2 psi across the check valve. All right, so let me cancel that. So those are the only two things that I did that is new in this example, and I already have results. And so this is still telling me that I had reverse flow through the compressor, but it may not be very much because I've got my check valve that is closing. And as you can see here, it tells me exactly when the check valve closes. So let's take a look at what's going on here. Let me go back to my graph results window. And if I was to load the tool pressure and temperature, we would basically see trends that look very similar to what we saw in the previous scenario. The values might be slightly different, but as you can see, the shape of the curves is virtually identical. Now, this is really neat, is if you're not familiar with creating graphs, it's pretty easy. And the green plus sign is where you can create a new graph. There is a lot going on here of things that you can do. And if you've never used the graphing capabilities before, this button is really important. What would you like to do? Well, this is an aid that will help you in creating different types of graphs. So how do you use this tool? Let's say I want to do a quick and simple graph. Well, this asks you what kind. Do you want to do a transient pipe graph? So do I want to look at the temperature at a particular station of calculation in a pipe? Or do you want to look at a transient junction graph, like the compressor speed versus time? Or do you want to do a profile plot? And so this walks you through the process of what you need to do to set up your graph. So if I do a transient pipe graph, it says expand the pipes. So let's say I want to look at the compressor. Actually, let's take all these off. So let's look at the compressor. Well, which pipe is that? Yep, pipe 2. So the compressor outlet is P2 inlet. And so if I'm following this here, it says expand the station and add it. You can add as many stations as you want. And then the next thing, select a parameter and units. And so I'm going to remove that. And so I've done that and then click generate. So I just created a graph. Now here's the next thing that is really useful is I might want to create this graph again later, especially if I'm doing different scenarios. And I don't want to have to redo these parameters every single time. That's a pain. Well, instead, what you can do is click on this button here, the folder with the blue plus sign, and that will file away your graph into the graph list manager, which is a really useful filing system for all of your different kinds of graphs. So here, I'm going to file this away into my graph folder right here that called My Graphs. I'm going to give it a name. I'm going to call it compressor, discharge pressure. And so that just filed away the graph into the graph list manager for the My Folders graph folder. And so you can create as many different folders as you want to keep your graphs nice and organized. Now, this is why it's really important to get familiar with how to use the graph list manager. It's because you can do something really cool like this, where you add all of these different types of graphs to this single graph folder, and you could double click on each of them and load them individually, just like so, but I don't want to do that. I want to show all these 3 graphs at the same time. So watch this. I can right click on the folder itself I could say load folder items in the same tab. Awesome. All right, so here's what we have going on is a lot of stuff, as you can see. What are we showing? I am looking at the pressure profile of 4 flow paths. So these are groups. I created groups by selecting flow paths on the workspace. So what I did was I selected a flow path just like this. I went to edit, groups, and then create, gave it a name, and then I had my groups. And I did that for all 4 paths to each tool. 1, 2, 3, 4. How can you be sure that I did it right? Well, if I hit F6 on my keyboard to pull up the select special, I can select my groups on the workspace. So I click on that drop down and say groups. Let's look at the group to tool 4 and select the pipes and click OK. Bam. So that's one of my groups. And the reason why it's really helpful to create groups is because when you create groups, you can look at multiple flow paths together at the same time. So here I'm looking at pressure, and this is tool 1 valve, tool number 2, tool number 3, and tool number 4. And you can see here how we have that pressure staggered at each one. The next thing that we're doing is we are showing the mass flow rate in pounds per hour to each tool. So we have the mass flow rate to tool 1, 2, 3, and 4. And what we're doing here is a animation. So we are looking at the 4 flow paths for pressure and flow, and I'm going to very soon click on the play button, and we're going to be able to see how the pressures and flow rates change throughout these 4 flow paths over time. As you can see, time, really helpful. Next, on the right-hand side, I'm showing my check valve CV. This way I can see, A, does my check valve chatter, and B, when does it close? So this is really useful because when you follow the time ticker that you'll see shortly here, and you see it approach this closure, once that valve slams shut, you'll be able to expect a response in the other graphs. And so this makes it really easy to understand what's going on when you evaluate things at multiple points over time. What I'm showing down here, this is the check valve pressure and temperature. Okay, so the red line is the inlet to the check valve for pressure and temperature, and the blue line is the outlet of the check valve. So if you follow the blue line here, you can see how our pressure increases, and then once that check valve slams shut, it just stays the same the rest of the transient, versus downstream here on the red line, that's after our compressor trip. All right, so let's go ahead and play the animation. And when you play an animation, the speed here is critical. You can make it go slower or faster depending on how fast you can track the transients going on. And I want to give a tip. When you're setting up your graph, it's really important to animate using the output file. Now, this is the only option here for xStream, but in AFT Impulse, there's a third option right here. Even in Impulse, I still like using the output option. And in order to do that, you need to make sure that in the MOC transient that you are saving all of the pipe station's output in the output file. Here's the reason why this is important, is because, let me collapse my quick access panel. When I click on play, and when I click play and we start animating, you see how that starts changing? Things will happen very, very quickly, and it can be difficult to capture what's going on. So it's really helpful to be able to pause your animation, and then you can back up time steps. That way, when you start to see your results do this, you can pause your animation and you can back it up to before all of the chaos starts happening to see what was going on, and that can help you better understand what's happening in your system. All right, so let's set that to default speed and maybe make it a little bit faster, and we'll stop the animation, and this will be able to tell us what's going to happen during our transient. All right, so let me click on play. All right, so if you're watching the first graph here, this red line, this shows how that first valve is closing. So when this mass flow rate drops to 0, that's when you're going to see your associated pressure increase at that valve. And then you'll see the same thing for the second tool and the third tool and then the fourth tool, one after the other. All right, so we play this, and so that valve is closing. It's shutting off the flow, and at 0.2 seconds, this valve is fully closed. So as you can see, we're just after 0.2 seconds. So this valve is closed, and this is where you can start to see a little bit of a transient response. And then this valve will start closing. And at the same time, keep paying attention to how the check valve is responding, as well as the pressure and temperature at the check valve. So now the second tool is closed, and it keeps going on, and now the third valve is just about to be closed. So the third valve is closed, and now we're waiting for the last one. So here's something that's important to pay attention to. You see this discontinuity at the branch? That's the sonic choking that we're seeing during the transient analysis. And so this is not something that you'd be picking up with AFT Arrow unless you know exactly what conditions to run your model at. And it still may not even occur. And so this is where it's really important to account for the wave propagation through your system with gas hammer or steam hammer. And so now we're just about to see the last valve close, and then you'll be able to monitor how the check valve closes and the response through it as well. So we'll keep watching here. So you can see how things are changing over time, and now that final tool is fully closed, and we start to see reverse flow, and bam, that check valve is closed. And so this is where you're going to start seeing a oscillatory effect upstream of the check valve. So here's the check valve right here, and this is where you can see some of that oscillating behavior as well. And also, this is when the compressor starts to trip. So at 1 second, that's when the compressor starts to trip, and that's where we start seeing our pressure decrease, which you also see with the red line right here. And as the pressure decreases, so does the temperature. And we just run this out for, the 5 seconds, and that drops. And this happens very quickly. And so now we're basically at atmospheric pressure, and this is just based upon the pressure that's trapped inside of the closed valves and the closed check valve. And there you go. So this is one application of where you would use AFT Xstream, and I demonstrated how you can take a AFT Arrow model and then open it directly in AFT Xstream in order to do your gas hammer or steam hammer or transient analysis. And one other thing that you would maybe consider using Xstream for is perhaps your instrument air system. And with your instrument air, if things are changing in your system, you want to be able to capture how fast your signal is going to transmit through your system. And so this is a good way of being able to see that. If you have a sudden event occurring and your instrument air is picking that up, how long does it take that signal to propagate to other points of the system? And so that's not something I've personally done yet, but one of my colleagues who worked at an oil and gas consulting company before was saying that would be another application for using AFT Xstream. So the thing is, even though you're not seeing gigantic pressure surges that could damage things like an AFT impulse, I mean, you could still see that in AFT Xstream, but the other thing that you'd want to know is how fast does it take those waves to pass through? So even if they're not very large, how long does it take your equipment to detect signals? And this is a critical application for using AFT Xstream in that case. All right. Well, that's basically all that I have for today. I want to thank you all again very much for joining us and listening in on the webinar. If anybody would like to try out AFT Xstream, certainly please feel free to contact us. You can reach us at sales@aft.com, and you can request to do a evaluation license, or you can try out the full version of AFT Xstream. And when you do, I highly recommend that you take the time to go to the help menu, show examples, pick your favorite units, and spend the time first to make sure that you work through these examples, because there is a learning curve, and you're going to want to make sure that you understand how to use AFT Xstream properly. It'll also walk you through instances to see what the effect of sectioning or using different fluid properties have on your run times and how much that may or may not change your results. Okay, let's see here. I got one question that came in. Is it possible to simulate a system with a heat exchanger? If so, is it possible to consider the variation of heat flux as a function of time? Currently, you do have the ability to model a heat exchanger, but it's going to be a fixed heat rate, and I'm not sure if you can change that over time. Let's test it really quick. Let me open up a new instance of Xstream here. So here's your heat exchanger, and so you're going to have a loss value. For heat transfer, you're limited to a steady heat rate. So you can do a steady heat rate, and then on the transient tab, this is where you can, yes, you can change the heat rate versus time. And so that's how you'd be able to do it at this point. All right. Thank you all very much for listening in. Take care and have a wonderful rest of your day and week. And we will catch you all in the next webinar.